Okay, so we got that working, and we just have to start up Logic Sim. There we go. I have the design already done at home, but I want to just kind of do everything from scratch here. Doesn't take that much time. Well, it takes a little bit of time, but not too much. Okay, but by doing this, it's also helpful in a way because now you know where those components are located, and it's also getting recorded at this point. So the way I do this is I deal with the registers first. So I look at all the registers in memory. We pick out 4 registers. So duplicate one more time. So now we have the 4 registers, and I need to space them out a little bit more. Here we go. And also, just for clarity purposes, I label these registers as A, B, C, and D. Okay, so now we have the 4 registers. To control the input into the registers, we need a decoder. So the decoders are inside the plexers, and you pick out the decoder here. For some reason, I did not turn on the other screen. I just have to be careful because now it's in a really bad state. If I am not careful, it will turn off this one and turn on the other one. So we'll see whether we can limit the emission control. There we go. Oh, okay. But if I don't press the power again, it won't turn off. So now this one is on, that one is turning on. So now we have 2 screens. Okay, but I'll just continue to use the one on your right-hand side. Okay, so we want to include enable in this case, but we want the disable output to be all zeros. Okay, not floating, but all zeros. And then on the other side, we have the multiplexers, and we need 2 of those because we have 2 inputs to the adder. And then the width of the multiplexer is going to be 8-bit wide because the input has to feed into the adder. The adder belongs to arithmetic operations, so we just pick out an adder here, and then we duplicate this mux. The mux does not need the output enable, so we can turn off the output enable here. There we go. And then the rest is really just wiring up this whole thing here. We wire up the output of the adder to become to the D port of all of the registers. So, well, I suppose I can use this line here. So all the D ports are connected, but which one is actually being changed is controlled by the enable pin. So the enable pin is coming from the decoder. Oops, not this one. This is the enable pin. So this guy goes here. This guy goes. Oop, did I miss one? There are only 3. Oh, there are 2 select bits. There we go. Okay. Now we have to fix the connections. There you go. Okay. Are there any questions at this point? Any questions about what the enable pin does, that sort of thing? Or how to print out the help from Logic Sim. You go to help, you go to library reference, and you go to the one that you need. Okay, let's say it's a multiplexer. So from here, I'm not really 100% sure how to print it out. Has anyone tried this? Try to select the content inside the help. Oh, it can be selected. So once you select the whole thing, just copy and then see if you can put it into a Word document. I use LibreOffice. I'm just trying to let you guys know how to. Okay, you guys. Okay. All right, so let's go ahead and try this. Create a new text document and paste it in. That works. Okay. So you can copy the help text from inside Logisim into a word processor, and then you can select which part you want to print and just delete the parts that you do not want to print. Okay, so that can be helpful. Yep.
Is there any way to copy it with the images, or?
Oh, that part I do not know. It did not copy the images. Ah, that's interesting. Okay, let me see if. It did not copy the image. Well, I'm gonna do that later because I don't know offhand, how to copy the image because I don't know how the image was stored to begin with. Sorry? I think these are probably HTML documents that is inside the jar file. So if you decompress the jar file, you may find the media files inside the jar. Okay. Let me address that question first because I think some of you may want to know how to do this. So let me give this a try. Okay, let's go to, I'm going to the downloads folder where the jar file is, and I can do an unzip on the jar file. There we go. So once the jar file is unzipped, I'm looking for probably HTML documents. Okay, these are the source. I'm just looking up resources. Those are properties, and then we have all the GIFs. Probably should have made a folder first. Oops. There we go. Now we can say find. Yep, they're all HTML documents. So if you go to the documents subfolder, okay, let me see if I can just do this.
I found PNG images of them.
Yeah, but you should be able to navigate into the folders. So let me see if I can do that. Okay. So go to doc/en contents.xml, go to HTML. Index.html looks really promising to me. There we go. So once you get to, okay, did you guys see what I just did? You go to the, okay. So in the command line, you can do this in Windows as well. If you try to do this in Windows, you have to rename JAR to zip first because Windows is kind of dependent on the extension to determine what you can and cannot do. So once you rename a JAR to a zip, or you can use a third-party unzip tool, then you can just unzip it. Once you unzip, you want to go to the doc subfolder, and then under that, the EN, or if you prefer other languages, okay, it's up to you guys. And then go to the HTML subfolder under that language. Yep.
It looks like the doc folder is also up on the SEN repository, so you just...
Or you can just drag that, yep. But in this case, you can use the one that is in production, and then just point your browser to the index.html document, click on library reference, and I think that should do the whole thing. Yep.
So taking apart a jar is simple as treating it like a zip?
Yep, because that's what a jar file is. A jar file is a Java archive, and they only use the zip utility program to compress everything. So now you can go to the library, you can go to, say, a multiplexer, click on that, and it's just an HTML document.
So I know this is off topic, but if I have a jar file, how do you keep people out?
You cannot. But a Java file only keeps track of the compiled bytecode and not the source code.
Oh, okay.
But people can easily reverse that because there are no decompilers for Java bytecode.
What if you turn it into an executable?
If you turn it into an executable, Java still needs the bytecode file to run. So there probably would be some sort of intermediate form of the Java bytecode somewhere that is still exposed. So anyway, I have just illustrated how to print out pages from the library references. So this can be helpful in your test because you can bring anything that is printed, including stuff from LogicSim. Is that going to be okay? Does everybody kind of understand what I mean by this? Okay. All right, so getting back to the design. Okay, so now we're getting back to the design here. So we want to bring all the outputs to the two muxes, because ultimately it is up to the muxes to decide, okay, which one goes to the adder. So all of these are really connected. The output of each register is connected to the input of the muxes. There we go. All right. And then the output of the first mux goes into the input of the adder, the first input of the adder. The output of the second mux goes into the second input of the adder. And then we have to specify a 0 as the carry in because we don't have any actual carry flag at this point. So we go to wiring, specify a constant of 0 to be our carry input. So the carry out we are not using, but since it's an output pin, we can leave it unconnected. It doesn't cause problems. So we are done with the upper portion of the design, except for the 0 here. So we want to make sure that we are not resetting the design. Only for this particular design, we're going to put a 0 into the reset pin of the register. In an actual processor, you would actually hook these up to a single global reset line of the design, so that when you assert the reset pin of the entire computer, not just the processor, everything gets cleared. Okay, but in this particular design, we are not going to do this because we're going to inject values into the registers when we need to test the design. So the other one left is the clock line, but the clock lines are shared by all of the registers. So they all go to the same pin, which goes to the system-wide clock pin. So we're going to connect all of these to a single global system clock pin, and that will be under a clock signal here. We just hook it up. All right. So we're pretty much done with the top part of the design that we talked about earlier in question number 7. So now it's time to work on the bottom half, which is your music box. So a music box has pretty much the same components as what you turn in for your homework assignment. We have an adder here, and then we have a register here, and then we want to connect the output of the register to one of the inputs of the adder. We want to specify a 0 on one side and a 1 to specify the carry in. So we go to constants, and since in this case it's not your homework assignment, we don't have any restrictions of how many constants you can use. I'm just going to use constants wherever it is convenient. So the 1 goes into the carry, which means we are constantly adding 1 to whatever the input specifies, which is the output of this register. And this is your music box register, so I still call it the music box register here. And then we take the output of the adder and we feed it back into the input of the register. And we also want this register to be always enabled. Okay, this looks ugly, but it works. There we go. And we want to make sure it is turned off. It's not being reset, so we want to bring this 0 to make sure that we are not resetting the register. And then the clock line of this particular register connects to the global clock line. But we do have to make sure one thing is this register has to update or trigger on the falling edge and not a rising edge. This is to make sure that we do not end up with a raised condition. If we have a rising edge with the music box register, then we can be changing the output of the ROM, which is not here yet. At the same time, all of these things are happening. So it can lead to a raised condition, which is not desirable. So we want to make sure that raised condition does not happen by changing the edge sensitivity of the music box register to falling edge, where everything else is rising edge. Okay, so now we have the ROM module, which is in the memory category. And I just used the default design. This is not. This is basically just a default with 8-bit as an address port, 8-bit for the data port, and we want select pin to be always on. So let's go ahead and do this. And then the address line just comes out of the register. Remember, it comes out of the register and not from the adder. Okay, so this is one thing that you have to remember.
Professor?
Yep.
Did we ever talk about demultiplexers?
No, because we have not had any need to use a demultiplexer yet.
So we won't have those on the exam?
That won't be in the exam. A demultiplexer is one where you can specify one single input and then specify which one of the output has the input. So it's basically a multiplexer, except it's the opposite direction.
Or like a decoder, except there's also an input.
Yes, it is kind of like a decoder where you can control the input. All right. So we got the ROM working, and now we just have to look at the data output, split it into the sections that we need. So now we need to go pick out a splitter, and we need to make sure the input width is 8. Split it into 4 parts, and the last pin is not used. So we have top, 1, 1, 2, 2, 3. So that's exactly the way we want it. And of course, I have no recollection of which pin needs to go where, except this pin needs to go. Oh, I'm running out of space here.
Where do you get the music box?
So this pin goes to the most significant bit. I do remember that one. And I think 4, 5 goes to the input, the select pin of the first mux. Doesn't look very good. I think 2, 3 goes to the second mux. And 1, 0, 1 goes into the decoder. There we go.
So is this our von Neumann machine?
Not quite. Okay, this is basically a subset of the entire processor. The von Neumann idea is based on this, okay, but we don't have an actual instruction decoder yet. Okay, so we have some of the concepts, some of the components of an actual processor, but not everything yet. But this is a fairly good, small subset, so that we can just use the music box and also the calculation engine that we talked about the other day to illustrate, concepts. Yep.
Will we ever construct a simple but full-featured CPU in this class?
Well, I have to kind of be mindful of the amount of time that we have in the semester, but yes, I do want to finish the whole design, but by stacking things, like gradually, because I don't want to give you the entire design first, because it's going to be overwhelming, because it's going to be big, complex, and there are components that we don't understand. So we're building the design, like one step at a time by introducing, okay, here are the registers. Okay, register bank is this stuff here, and then we have the quote-unquote ALU. Even though in this case it can only do addition, what we talked about today is just like, oh, we can just add additional things that can do calculations, and have a mux to specify which one becomes the output. Then we have an ALU that is capable of addition, subtraction, whatever you want to specify, right? So that's what I want to do, is to introduce those concepts one by one to make the design closer and closer to an actual processor. But even as it is right now, we can do some fun stuff already, like what we talked about in class. Okay, so if I remember correctly, the instructions are CF and DF. Okay, and I believe that I preserve the wiring of everything else. So we've specified this one as, oops, CF, and then the other one as DF. Okay. And it looks right to me. All right, so as it is right now, we are already, quote unquote, running the code because the output of the ROM is already active. And you can also see that the clock signal is a low at this point, which is the assumption in the question, in question number 7. So we want to see whether the design is actually working or not. Since all the registers have zeros, it's not helpful. So we're going to inject some values into register A and register B as well as register D, just so that we can tell whether it's working or not. So we'll put a 0, 1 into register A. We'll put a 1, 0 into register B. And then D can start with, let's put a 4, 0 into D, okay? So these registers come started with specific values. So once you have values in the registers, you can actually, quote unquote, probe this design and see whether the registers are outputting the right content or not. Okay, I'm not sure how many of you have tried this out, but once you're in emulation mode, which means you're using the finger tool, you can actually have the finger tool to touch a wire. It will show you the actual signal on the quote-unquote wire or bundle of wires, which is really helpful. So in other words, what I'm saying is, if you click on this wire, it tells you that this quote-unquote wire, which is a bundle of 8 individual bits, has a content of 0000001, which is correct because that's the output of this particular register.
What's the /1?
The /1 is just saying, okay, this is, one is in binary and then the other one is in decimal. So you can look at the other one, which is this one here, and it tells you it's 00010000, which is in base 16, in base 10, a 16. Okay. Is that okay? All right. But what I really need to know is whether the muxes are doing what they're supposed to do. Okay. Am I seeing the content of register A from the first mux? Yes. Am I seeing the content of register D from the second mux? Yes. Okay. So now I can expect the result here to be the sum of these two. In other words, I can expect the sum to be 41 in hexadecimal or 65 in decimal, because the calculation is instantaneous, quote unquote instantaneous. As soon as you change the input to the adder, the sum is presented to the output, which is supposed to be the case here. So we click the output here, and it is in fact 65. So everything looks good so far, okay? So we trace the 65, which is the line that is thicker, which is also really helpful because it makes it easier for you to trace where a particular, what we call a node, is connecting. This is a wire, but when you look at everything that this wire connects to, in other words, everything that is kind of thicker at this point, it is called a node in electrical engineering, because electrically they're all connected. So we want to find out where this node connects to. So it connects to the input of all of A, B, C, D. But in this case, we know D is selected because in this case, because it is a single bit, a light green is a 1, a dark green is a 0. So we know this particular register is selected. It's not updating yet because the clock is still low. It will only update on the rising edge. Are we doing okay so far with this? Yes? Okay. So that means if I click on the clock line, then we should observe one change only. Okay. On rising edge, there's only one change, which is the content of register D should become 41, which is 40 in hexadecimal plus 1, which is in register A. That's the only change we should see on the clock transition. So there we go. So now the clock line is high, and we have already made changes to register D. It is now a 41, If I click on the clock line again, it will fall. We will have a falling edge. And which register is sensitive to falling edges? The music box register. Very good. Okay, so the music box register is sensitive to the falling edge. Now you can also see, how it's going to be updated by clicking on the wires. In other words, you look at the output of this particular adder, it is a 1 already, which means the input to the music box register is already seeing a 1. It is not updating yet because the clock is now a high, but when I click it low, then it will update, okay? But that update will change a few things because it will change the music box register to 0, 1, right? But the output of the music box register connects to the address port of the ROM. So as soon as I click on the clock line, then the next location DF will be selected, will be highlighted in the ROM, which changes the output lines of this particular, of all the signal lines, and it will change so that register B will feed into the top box. Okay, so all of those changes should happen, and when I click the clock line, click just like that, exactly. The register gets updated to 0, 1. DF now becomes the output. So as a result, the first mux is now has the output of 16 in decimal, or 000110, excuse me, 00010000, which is coming from register B. And then the second mux is still taking the input from register D, which is now 41, okay, which is 65 in decimal. So we can verify the design step by step by probing the wires, just to make sure that, okay, I think this should be the output on this wire, I think this should be the output of this wire, and we can double check everything before we actually clock it. So the output here should be the sum of 65 or 41 in hexadecimal and 10 in hexadecimal, so that it should become, what was it again? 51 in hexadecimal. 51 in hexadecimal is 5 times 16 plus 1, which is 81. Okay, so we check the output of the adder, make sure this is 81. It is 81. Okay, so that's good. And we also want to see which register is going to be updated. Okay, you look at the enable pin of the registers and see which one has a high, and register D is the one that has a high. So that means when I have a rising edge by clicking on the clock line, then register D should be updated to a value of 5, 1 from its current value of 4, 1. Okay, so let's do that. Click it, and you can see register D now has a value of 5, 1, which is the sum of whatever it had, which is 4, 0, plus 0, 1 in register A and 1, 0 in register B. So the operations were in fact correct based on what we talked about during the lecture time. Yep.
Your music box updated when your status changed from 1 to 0, but register updated when it's changed from 0 to 1.
Correct.
How you did it? How you done? Why it's updated in different ways?
Because I want to avoid a race condition. A race condition is one where, depending on the timing of things.
You said music box like not race condition, but different condition, right?
Right, because the moment this register changes, it will change the output of this ROM. Right?
Yes.
So now we can potentially have a race condition, because when you update the output of this ROM here, okay, as this is getting updated, we are changing the control signals to the decoder, to the muxes, and so on and so forth, right?
Because when I done my music box, it was updated from 0 to 1.
Right.
So you did something different in your music box.
This is different because in your music box homework assignment, are you talking about the music box homework assignment or this design?
No.
So in the music box homework assignment, the only thing you're controlling is a 7-segment display, which is not edge sensitive in any way, right?
Okay.
So you cannot end up with a raised condition. But in this case, we have what the music box is controlling is something that is also edge sensitive. And that becomes a problem, because if I use a rising edge on the music box register itself, then we can see changes to the output of the ROM at the same time as the rising edge into the registers. So now it becomes a race condition, because if these lines, some lines are slower, then I can have the wrong register selected when I capture the output of the adder back into register D.
Okay.
But by doing it the other way, by using a falling edge on music box and a rising edge on all of the other registers, I allow half a clock time for things to settle down before I update the other registers, which is plenty of time. Because I don't want to end up with a race condition where the wiring, the length of the wire, the capacitance on the wire can change the result of the whole design, and this is one way to make sure that happens. Does everybody understand how, just conceptually, how you can end up with a critical race condition if the music box register itself is also updating on a rising edge? Let's see what happens. Okay, we cannot see in the simulator because the simulator cannot simulate delay effect of lines. But if you just think about it, let's see whether we can just kind of mentally simulate this kind of thing happening. If the music box register is also updating on a rising edge, then the rising edge of the music box register will change the address line, right? And then the first thing it will do is it will select the next location, and that becomes the output into the control lines of the decoder and the multiplexers. Is that okay? But at the same time, that clock, that rising edge, is feeding into all of these registers as well. So all of these registers will just take, whatever the input is, which is the output of the adder, we'll just store that. So now you have a condition of, okay, which one is faster? Can we update the decoder so that we select the right register before it updates?
Maybe, maybe not.
Maybe, maybe not. Can we specify the input of the muxes so that the adder is actually adding the right result before we capture the output?
Maybe, maybe not.
Maybe, maybe not. So we end up with multiple race conditions when we use a rising edge on the music box register. Is that okay? But by changing the edge sensitivity of the music box register, we avoid all of these problems. Yep.
Why do we call it music box? Like, why don't we just call it counter or memory selector, or like something that, I don't know, says what it actually does?
Because, well, it has to do with the homework assignment, because the homework assignment is
Was the counting that?
because it's just a music box. Because the way I look at this is these things are just rows of pins on the drum.
And
this is a music box mechanism. You just wind it up and let it play, and when it plays, it doesn't have any intelligence. Okay, it doesn't really think about anything. It's like, okay, I want this pin to be high, and that pin to be low, that pin to be low again when this pin goes high, and so on and so forth. So it's really the same thing as a music box, except you're not plugging those times.
You're selecting memory locations.
Exactly. You are not exactly selecting, well, the output is used to select the memory location, but the output of the ROM is the actual critical plugging. But what are you plugging? What are you changing? In this case, you're changing the select pins of the multiplexers as well as the decoder. And by sequencing those changes, now you can accomplish different things, like adding this register to that register and so on. So that's why I kept the name of music box, to connect to a homework assignment that you guys have done already. But you're correct. The technical name is not a music box register.
It's like,
The technical name is a microcode program counter.
I prefer music box.
It's a microcode program counter, but since we haven't really talked about what is microcode and stuff like that, we are examining what microcode really is and why it is important as we talk about this. But I don't want to use the word microcode because we don't really have the decoded mechanism to decode instructions yet. But we'll get there. We'll have a lot of fun with that.
oh, I'm sure it'll be fun.
Are there any questions about this particular design? Or the question itself, question number 7? Now this is actually, it is the core of one of the most elemental instructions, which is really just saying, hey, I want to pick up these two registers, add it, and store the result into that register. That is one of the most basic instructions of any instruction set of any processors, okay? So what do you think would be the other types of instructions that you would need? Just in terms of concepts, we're not talking about
Copy.
specific opcodes.
Copying.
Copying, okay, very good. So copying is good. What else do you think would be useful instructions?
Send data on a specific output. Like
Save.
a monitor or a keyboard.
Saving data?
Saving data? Okay, so that's a great idea, okay? Because at this point, what you're seeing here, everything in this picture are a part of the processor. Where's RAM? RAM is external to this. So we need some kind of circuitry to interface with RAM as well. In other words, we need some kind of mechanism to say, hey, I want to access the content of that location in RAM. I want to store the result, or I want to store the value of this register into that RAM location. Or the other way around, I want to read that RAM location and then store that value into this register. We don't have those mechanisms yet, but you can see how we can expand this structure here to also interface with RAM. What else? What else do you think is important? Especially when we're dealing with the von Neumann architecture. What is special about the von Neumann architecture? What makes it different from all the other architectures prior to von Neumann?
Data and instructions.
Instructions are stored in RAM, right? Okay, so when you store instructions in RAM, so you'll be getting bytes from RAM and say, okay, this is specifying add, this is specifying subtraction, and so on. What do you think are the different types of instructions that you will need? The ones that do calculations, okay, adding, subtracting, and stuff like that, we kind of talked about it. The ones that can copy things, like from register to memory, from memory back to registers, those are useful too. But at this point, with only those type of instructions, you can only write a program that is a straight line. It can do calculations, it can store values, but it's a straight line. In other words, you don't have branching. Okay, you don't have conditional branching, you don't have loops of any kind. So what do you think is needed for loops?
Iteration.
Okay, well, but you have to kind of remember put it in the context of the von Neumann architecture. In the von Neumann architecture, instructions come from memory. So that means inside the processor, well, oh, okay, this is the music box, but there's a program counter that is on top of the music box register here. Okay, so this music box register is the microcode program counter. But the microcode themselves would affect a program counter, which affects which instruction in RAM you are going to execute next. So we are not quite there yet, okay? But I'm just giving you guys a preview of what is yet to come. With branching, which is really just changing the program counter, is useful because now you can loop. But you can only have infinite loops. Because upon execution of that instruction, it's always going to change the program counter back to that location over there. So you have an infinite loop. So what do you think is needed to break out of infinite loops?
Conditional statement.
Conditional statements. But how do you think conditional statements are implemented at this level? Think about.
I would have a section in the RAM that selected the pin to clear what I was doing.
But you need a way to decide whether you want to continue with the current path or whether to go somewhere else, right? In other words, you need a mechanism to give you a Boolean value and a mechanism to say, oh, normally I go over there, but this time I want to go over there. Yep.
Wouldn't a jump be sufficient?
Hmm? But you don't want a jump to be unconditional. So you need a conditional jump. Sometimes you want to change the program counter to a specific location. Other times you just want to increment to whatever is next to
Keeping track
jump.
of true false.
Yep, exactly. So you want something that is either true or false, that is after some kind of calculation. When you think back in
So
C
like
and C++,
check.
C and C++ expressions, conditions in a conditional statement, what is the simplest thing that can give you a result of true or false?
If else.
Sorry?
Or
Just a Boolean variable.
A Boolean variable, but the Boolean variable by itself needs to get the Boolean value from somewhere, right?
then.
What is inside the
Zero.
parentheses of an
Zero
if? That's
or
the
one.
question. Huh?
0 or 1.
0 or 1, but the
Comparison?
0 ones are constants.
Comparison.
Comparisons, exactly. So comparisons is the most basic form
Oh, man.
of.
It's like so hard thinking this level.
But comparison is the most basic form of a Boolean thing that can help you decide which way to go. Is it greater than or not? Is it equal? Does it equal to or not? Okay. So at this point, we have one single construct that can be useful for comparing already. Okay, what is comparing? I'll give you two choices.
Check
Is-
the state of something if it's on or off.
Okay, listen to these two choices. Do you think comparing is adding, or do you think comparing is subtracting?
Subtracting.
It's subtracting. Okay,
Because
very
if you
good.
subtract them from each other and they equal 0, then they're equal. If you subtract them from something they equal
Right.
1, then they're not.
But there's one thing that we talk about in a subtractor that can already give you some information after a comparison.
borrow.
The borrow flag. Okay, very good. So the borrow flag is important because after a subtraction, you look at the borrow flag, and then you can have instructions. We haven't talked about the microcode to do that yet, but you can have a single bit or a single instruction that looks at the borrow bit after a subtraction and say, if the borrow flag is a 1, this is what we're going to do. If the borrow flag is a 0, this is what we're going to do. So we'll get to all that stuff. I'm just giving you guys a preview because we are kind of on this topic. And we have already seen the mechanism to do that already. Okay? How can you use a single borrow bit to determine where to go next? What is the one mechanism that we have talked about already in terms of gates and components in logic sim that kind of have the same effect as sometimes we want to do this, other times we want to do that. It has one single input to select one of two paths.
Oh, a gate. No.
It's a reverse. It is a mux, okay? It is a mux, okay? So remember what a mux does? But this time, let's talk about a very simple mux because we are talking about a single select bit. There's a one single select bit here which is borrow out from a subtractor. Okay? So now you can say one alternative is here, one alternative is here, this is the output. So one can specify a specific location that you want to continue to execute, the other one specifies just the next location based on the adder. So that will give you the most basic mechanism to do something that is conditional after a subtraction. So we'll get back to this again, okay? So for people who are not here, they will see this again. But for you guys, you may not understand this entirely at this point because I'm just theoretically saying stuff that's remotely connected to question number 7. But eventually when we talk about this, then you go like, oh, so that is the mechanism to do it.
Are you recording?
I am still recording. but not stuff on the whiteboard. So the essence of this entire discussion is to do branching that makes a program smart, because that's what you need to do conditional branch, conditional statements, and loops and stuff like that. It all boils down at the gate level to multiplexers. And the input of the selection of the multiplexer would be certain flags that reflects the result of a comparison or a subtraction. The only one that we have seen so far is the borrow out after a subtraction, but there are other ones as well, as we will see later on in the semester. Are we okay so far with this?
Mind blown.
Well, it's just a preview of what is yet to come, okay? But by the time we talk about that stuff, we'll basically go back to this discussion and you guys will go like, oh, so that is how everything is connected. In other words, we are designing a processor from the bottom up. We look at things that we need to do, and then we say, okay, give us the simplest thing that we want to do. Let's see how we can do it with the components that we have talked about. And then we stack something on top of that, and we stack something on top of that. I'm not a very top-down person like most of the other professors. I'm more of a bottom-up, look at how did we start this entire semester? What was the first kind of device that we talked about? Transistors. We started off with transistors. So we built everything from transistors to NAND 2s and then to OR, and NOT, and then we talked about the other gates, the adder, the subtractor, and then we talked about the flip-flops, the SR latch, and then we talked about memories and stuff like that. We even look at the decoder in terms of gates. So we're building things from the bottom up. All right. Any questions?
I like that way.
Some people like that, some people like the top-down way a little better. But the bottom-up way, I think, is easier. In a class like this, it's easier. Any questions about the questions in the exam?
There's also another practice exam on how.
There are some additional practice exams on Moodle, but I am only focusing on one because the way I teach this class has changed a little bit. So the other practice exams is not as relevant as the one that we just talked about. So when you look at the notes here, there are two more practice exams. This is one, this is the other one. And with this one, well, we should be able to answer these questions as well. It's just that we really never focus on these in this class. What is this? Identify this schematic and label the pins accordingly. Okay, yeah. X, exclamation point Y, exclamation point X, Y. What is that? And this is a OR.
That's a,
No. It's not a latch because a latch has feedback.
That's the first
That's a
bit
result.
and a
There's a result. Okay, very good. Good job. So this is the R of these two pins. Good job. What about this guy here? This is just a regular N, which is XY.
Carry in.
That's carry out, right? It's a carry pin.
Oh.
But it specifies the carry function, right? So this thing as a whole is called it has a result, it has a carry, it is a half adder. Okay, it's a half adder. Okay? As a half adder, these are the two input pins. This is the carry pin, this is the result pin.
Result.
I guess I was
Identify the schematic and label. Oh wow.
We are just reading the equations, but in terms of gate logic in the schematic.
So these pins are not actually both X1, 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 X1.
No.
No, the X1 is really just
Be like
telling you
X,
the width
Y,
of the pin.
R, and
Yep.
C out.
Yeah, the X1 is really just the
Whichever one.
width of the bit.
Okay, so
How many bits?
You would say X, Y, R, and C out.
Yeah, but they have
So in the next question, X, Y, C, R. Okay, these should be fairly familiar now. Okay, this is a carry, result,
It's a full adder.
This is a full adder. Very good. And then this becomes the actual carry of a full adder. This becomes the result of a full adder. This is carry in of a full adder. Okay. And then the next question. See, I cannot ask this question this semester because I have not gone far enough to
Holy
talk about the
shit.
processor itself. But you can still
This is the
identify certain
practice
things.
exam. It's like, yeah, if you can solve this, you're good.
But this one, if you think about it,
Actually, this isn't doing that much
we
complicatedness.
should still be able to identify certain parts of this that we have seen already. What about this part here?
That little section
That's the
is
music
doing
part.
This
the
part here,
counting.
just this
Yeah.
part here.
That's the music box.
That's your music box. It's the music box engine. This part is the music box engine. But this one is more complete because it can actually interface with memory, and then the registers are all stored here. You know, the stuff that we saw earlier today, all the registers, the two muxes, and also the decoder, they're all contained into this one little chip. Okay, that's why we don't see the details. And then this is the ALU. This is the actual ALU where you can select what operations to perform, and has two input ports that are coming from the register banks.
And that RAM is storing the results of the
The RAM is
calculations.
connected so it can store results.
It's storing the results that's telling it to
Yeah.
process.
Yep.
I don't know.
And then you have the instruction register okay, this is the program counter. This is what actually dictates where is the next instruction to execute in memory. This is the program counter. Remember what I said a little bit earlier? You can use a mux to determine which way to go. Use the mux.
I see. So
So it's saying,
the
this
next
is saying
one.
if the result to carry out the
Well,
result of whatever calculation is wrong.
But you can see the program counter has kind of the same thing as the music box register. It has an auto increment mechanism. See this part here? That's the same auto increment mechanism. But it has a mux here because sometimes we may not want to continue with the next instruction. We might want to say, hey, just go straight to that location over there. That's why we have a mux, so that we can branch. Because otherwise, all you can do is to keep going in one direction. But this allows you to say, hey, most of the time, we want to take the output and use that to increment the register. But sometimes we want to use something else to tell me where else I need to go to continue the execution of the program. And therefore, we have the ability to do branching.
So the instruction register grabs whatever is the instruction from that place in memory, and then the next, the program counter says what's the next instruction register after
Right.
this
It will
operation.
auto increment. Yep. Yep. Exactly.
Oh.
But we haven't talked about it yet in this class. So we're building the processor as we speak. So far what we have talked about in this class is the microcode engine, which is this part here. We talked about the register bank, which is this part here. We talked a little bit about the ALU, which is this part here. So we have only covered those specific parts with this semester. So that's why I cannot ask you this question this semester, because we haven't really gone through this design.
So some semesters you get to this before the first exam?
Because I did not, because in that semester, I did not explain SR latches, D flip-flops, and the edge-sensitive D flip-flops.
Was there a reason why you decided to explain it now, or?
Well, I wanted to explain it now because, well, first of all, I personally is fascinated by it, and two, I really think it's really a good thing to design to explain it, because it's made out of what, NAND 2 gates, right? But out of NAND 2 gates, you can make the smallest unit of memory, and I think that really is one, interesting, and two, it's a good way to apply what you learned about just logic gates. So by changing the ordering and also the topics, sometimes I can get this far, but not presenting flip-flops and latches. And then with this semester, I explained memory in a little bit more details, but then we couldn't get as far in terms of the inside of the processor. And then the approach is also different. With this semester, I finished the design first, and then I tried to explain how it works, which is a top-down approach. With this semester, the current semester, it is the bottom-up design. I explain all the smaller parts and say, okay, what can we do with these things? Okay, we can do something minimal, like your exam question number 7. We can add registers and then store the result back into registers. but then we will stack more things on top of that to eventually become the processor. So the way things are explained is different in this semester.
I like the bottom approach better. Like understand the itty bitty pieces first, and then because it kind of gets you like
It's a more of a
thinking
Lego
of what
approach.
stuff you could do with what you know already.
Right. It's more of a Lego approach.
Yeah, because if I
like
saw
it.
this, if I saw this the first week, I would have.
Drop the class.
Yeah. That or freaked out. Both, probably.
Freaked out and drop the class.
Yeah. Because I would be so worried about I don't understand any of this that I wouldn't even be focusing on the lectures. But when you start off small, you go through, you build on, and then you're like, oh, now this makes sense. You start connecting everything together. Then you have a computer.
And also it brings you the satisfaction of knowing that everything can be done with transistors, because they all boil down to gates, and the gates can be done with transistors. So that to me is is kind of the most important part. Is really just illustrating. This is computer architecture and assembly language programming combined into the same class. And for those of you who want to know, where, what dictates, what they need to teach in this class, all you have to do is to go to the ARC website itself. And you can do this with most of your other classes too. And it is taking a long time to load. That is interesting. Okay. Is internet okay? Yep, internet is okay. It's just that the ARC website is not. Okay, let's do it one more time.
It's not just you.
It's the ARC website. Got
Where
hacked.
were you going to go to?
Huh?
Where were you going to?
I'm trying to look up the CID of classes, especially the CID of this class, but I want to show you guys how to do it so that you can actually see, okay, so what kind of topics should be covered by a class for transfer purposes. So this is kind of important. Well, let's go to Saxony because I think they have the same thing. Nope, the entire Los Rios is, nope, Saxony is up. Okay, so if you go to their schedule, because you can get to the schedule of ARC from their schedule. Class schedule, there we go. And then from here you can go back to the ARC schedule. And you can go to current class schedules, go to here.
What
And
does CID mean?
CID is really just literally course ID, course identifier. So we want to look at here, go
When
to...
you find that, what can you do with that number?
I'll show you exactly what I'm going to do here. So only some classes have a CID, like only transferable classes has a CID, like this one. We have a CID Computer Science 142. So I'll do a search for that. But if I go back here, cisp310 on the other hand has no CID because it is quote unquote not a transferable class. So it has no CID to match it. So when you look up CID comp something, you can bring to a you can go to a descriptors website, which is cid.c-id.net, and over here you can go to descriptors, and in descriptors, let me see here, comment, view. Okay, view final descriptors, because all the descriptors for computer science are already finalized. And what you do is look for the descriptors based on department. So you go to computer science. There are only 5. And then you can look up these things. So I cannot scroll up any further, so people who are sitting in the back may find this a little hard to read. 112 is programming concepts and methodologies. I think that is the same thing as CISP360. So when you look up CISP360 in the schedule, it probably has a CID of comp 112. And then concepts and methodologies would be, one is object-oriented programming, it's 400, and the other one is 430, which is data structure. And then with this class, it's 142, and then 440 maps to 152. Okay, so let me click on one of these, the one that is relevant to us. Okay, it's called Computer Architecture and Organization. So the minimum units is 3.0. We have 4 because we have the lab component. But the course content is basically dictating that I have to go over all of these topics. So we have to talk about bits, bytes, words, numerical data representation, number bases, which we talked about, base 2, base 16, that sort of thing. We haven't talked about fixed and floating point numbers. We will talk about signed numbers next. Representation of non-numerical data, we'll touch on that, ASCII code and stuff like that. We'll talk about records and arrays, organization of the von Neumann machine, which we spend a lot of time on. Control units, okay, we have to finish the processor before we can talk about what is fetch, decode, and execute. Instruction sets and types, since we're working on the processor from the inside out, that's going to be pretty easy to explain because we're explaining what is inside the processor when we execute certain instructions. And then we'll talk about assembly language programming, instruction formats, addressing modes, subroutines, and stuff like that. But this is important because this particular CID descriptor, we call it a descriptor, is quote-unquote agreed upon by all community colleges, CSUs, and UCs. So when you get your transfer degree, it is basically saying that you have earned a grade of C or better with these topics introduced. So the other universities, the 4-year universities, will basically say, okay, you took cisp310 from ARC, which matches the descriptor that we are displaying on the projector. So the 4-year universities will know, okay, so you at least know all of these topics. So the idea is for the entire state to share one single transfer agreement, which is basically saying, okay, if the degree that we offer include all of these descriptors as a program, as a degree, then we become an eligible transfer degree. And once you earn a transfer degree, then you'll be eligible to transfer to any CSU and any UC. But they get to pick which of the applicants to accept based on GPA and many other factors, but you'll be eligible. Is that making any sense? But there are certain universities who are not agreeing to play by these descriptors. I'm not going to say which one. Most universities agree on these descriptors already. Sac State, no problem. I think UC Davis, for the most part, no problem. Chico, no problem. San Luis Obispo, no problem. So all the most important ones in computer science do not have a problem with these descriptors. But some of the UCs, have not agreed on these descriptors yet.
UCLA?
UC Berkeley and UCLA, I believe, are not on this yet.
Yeah.
So you talked to those folks over there?
Actually, he didn't show up on transfer day.
Okay.
It's
It's Berkeley. Well, that's why Berkeley does not even refer to themselves as UC Berkeley. How do UC Berkeley graduates refer to Berkeley? Cal, exactly. Because that's the only university at the time of California, the only public university. So Cal. All right. Any other questions I can answer?
I've
Yep.
got questions from 440.
Uh-huh. All right, so I guess I can stop the recorder.
And then understand all the code.
Yeah, what everything
Yeah, I was
does
doing my
before we
assignments
can
and I think
figure
I know
out.
what I'm
I'm wondering
doing,
if
but I
you could
also think I
just-
don't know what I'm